Okay, this is lesson 8. This is geotechnical engineering design. In this video, I'm going to cover the topic of foundations at a very basic level. So we are going to start talking about the effective stress, the soil strength, and the failure criteria in soil mechanics and in geotechnical engineering. So these are three of the most fundamental concepts around foundations when you try to design or you're trying to verify if a foundation is in good conditions. The first concept that is important to understand and is important to take into account is the effective stress in saturated soils. So the effective and total stress have a definition, and you know the total stress is just the stress that is produced by the self-weight of the soil or for external loads on the soil. And the effective stress have a very simple definition, which is basically the difference between the total stress, sigma, minus the pore water pressure. As you see, the effective stress, of course, is an stress, so the units will be, for example, kilonewton per square meter. And the total stress are an stress as well, and of course, the pore water pressure is as well an stress, but it's a particular type of stress because it's an spheric stress. We are going to discuss this in future videos. So, but the important thing to remember is that the definition is simple, but the importance is huge. So again, the effective stress is equal to the total stress minus the pore water pressure. So we are taking into account not only the loads produced by the weights of the soil and external forces, but the effect of the water pressure in the pores of the soil. Remember that this effective stress definition, or this effective stress concept, has been used for a while now because it was discovered by Carl von Terzaghi, and so he formulated this principle in 1930s. So it's a lot of time already, almost a century. And the following principle was stated in this way: so that the formation of a soil depends exclusively on the changes of the effective stress. So this means that in soil mechanics and in geotechnical engineering, the effective stress is what matters. The total stress can be used in certain circumstances, for example, when you do have water present, so the pore water pressure is equal to 0. But in this case, when the water is not there, we say that the effective stress is equal to the total stress, because mathematically this is true. If the pore water pressure is 0, then by the definition, the effective stress will be the total stress minus 0, so both of them will be equal. Remember that for this principle, this important principle, the assumptions are huge. We are saying that the solid particles are undeformable and the water is incompressible. In the civil engineering application, this is true because certainly the water is almost incompressible and the particles are almost undeformable. But remember that this is necessary to have consistency in the mathematical equations. So, what about the soil strength? The soil strength is the second topic, the second definition I wanted to review again with you because it's important. We need to define a way to say when a soil reaches its strength. And in soils, the most famous or probably the simplest approach we can have is to consider the soil strength that is expressed by this equation you can see here. So there are three different cases. The first case is when you have clays and the situation is drained. It is to say there is a mixture between clays and sand, and the sand is producing or is giving this permeability that allow the water to flow. And this is the reason why we say this is clays, but the situation is drained. And the expression, the general expression for the soil strength is that the soil strength tau u, this u is for ultimate, is equal to the cohesion plus the effective stress we have defined previously, multiplied by the tangent of the angle of internal friction phi. All of this has this prime in here just to represent that this we are working, for example, in terms of stresses, in terms of effective stresses, and these are values that are modified usually using certain standard, like for example, the Eurocode 7 we use in these videos and in these notes. When you have the case where the clay is undrained, we are saying we are in the situation where there is only clay. The clay, when it's saturated, is almost impervious. It's not perfectly impervious, but it's almost. And in this case, we are going to lose in our expression the second term because there is no any sand present, so there is no any angle of internal friction to be considered. Or what is this? It is to say, the angle of internal friction to be considered is 0. And because of this, we are going to lose the second term of this general expression. In this case, we are going to have a simple equation where the ultimate soil strength in terms of the shear stresses is equal to a value. For example, this is called SU or CU, two ways of saying the same thing, which is the undrained soil strength when you have a clay. So this is the undrained clay strength when you don't have any sand present. Finally, the last case is when you have a sand and the situation is drained. So this means that you have only sand. So the clay is not present in your soil, in your case. And this is the reason why we lose the first term of this general equation in here. And we work only with the second term, where you consider the effective stress produced by the weight of the sand or the external loads. And you have as well the multiplication by the tangent of the angle of internal friction as you had in the general expression. Remember that analyzing the units we use in this equation is important. So the shear strength, which is the shear stress, is expressed, for example, in kilonewton per square meter or in newton per square millimeters. The cohesion is a stress as well. The effective stress is, of course, a stress. And the undrained shear strength are stresses as well, as you can see in the unit in here. The only units that are not stresses are the angle of internal friction, that in this case is degrees. But because we apply the tangent of an angle in degrees give us a number which is adimensional. So this factor in here, tangent of phi prime, is equal to a number without any units. Then our expression of the soil strength, which is a stress is equal to a stress plus a stress, is consistent. The failure criteria is can be represented in a space where you have in the vertical axis the shear stresses and in the horizontal axis the effective axial stresses, sigma prime, and this is tau. And this equation in this space, as you can recognize very easily, is the expression of a straight line. The straight line on top and the straight line at the bottom are defining this area between these two lines, this area where the soil is in good conditions. So if we are inside this area, we are going to be in good conditions because we are not reaching the soil strengths. The soil strength is defined then by these two lines in here in this Mohr-Coulomb failure criteria approach we choose to work with. Remember that in this space you can represent any state of stresses in every point of the soil mass. For example, this can represent this element in here, this square, can represent the state of stresses in a point under a foundation. So in this case, we are representing the horizontal axial stresses as sigma x, the vertical ones as sigma z, and we have a set of shear stresses as well. So we are saying in this criteria that the soil will fail because of the shear stresses. It's not going to fail because the axial stresses in the horizontal direction. It's not going to fail because the stresses in the vertical direction, but it's going to fail because the shear stresses that are produced in any point of a soil mass. In our space tau sigma prime, we can have, for example, a situation under a foundation where we have a state of stresses that define this Mohr circle in here. So remember that the Mohr circle represents the infinite state of stresses in every direction around a point in a soil mass or in a structure, for example. So as we can see, because these Mohr circles represent all the possibilities in terms of the state of stresses in the soil mass, at this point, this situation is a safe situation, is a good condition, because we are inside the area defined by the failure criteria. For example, if we reduce the value of the horizontal stress, we are going to move this point, and of course, the Mohr circle will be greater, because we are considering here that these 2 points are the principal stresses anyway. So, but the idea is to see that if we modify the state of the stresses, we are modifying as well the Mohr circle. So the bigger the Mohr circle, the closer we are to the failure. If you reduce more the value of the sigma x, for example, and we touch with the Mohr circle these two lines that define our limits in terms of failure criteria, we are going to reach a state of stresses that make the soil fails in this theory. So we are going to have at this point a pair of axial stresses and shear stresses that will produce a failure in our soil. This failure will be produced in some direction. It's not necessarily the direction that originally we took into account to construct the first Mohr circle, but certainly this will happen and can happen simultaneously in several points, or can happen only in one point of the soil mass. But in any case, if we follow this theory, we are going to have a failure because we have reached this point in here where we have the limit of our strength for our soil. And this is what happened in reality. If you see, for example, you were wondering probably when you see this equation why the failure criteria is defined in terms of shear stresses. Why the failure criteria is not defined around the axial stresses or around a combination of stresses. Why is specifically defined as reaching this value of the shear strength and not any other. And the reason is because the soil is a material that tends to fail when reach certain value on the shear stresses. Remember that soils, for example, in a foundation, let's see this example, because the forces are usually compression, there is no major problems in terms of the compressive stresses because the soil is certainly good taking compression. We never action on the soil with axial tension stresses because we know that the soil is formed by particles, and particles are not able to take tensile stresses. So we certainly try to compact the soil to produce a better strength, and we apply forces of compression because we know the compressive forces are taken by the soil. But the shear stresses are the stresses that make the soil fail at the end of the day. Because, for example, in this structure that was failing because this catastrophic failure in the soil, as you can see here in the picture, is because the mechanism is a mechanism we studied before for slope stability, and it's a rotational mechanism. For example, if you try to reproduce what's happened with this structure in the lab, you will see that in the soil is defined this line of failure, and this mechanism of rotation is produced. And then we know that the shear strength was reached in this line, and this is the reason why the soil has failed under the foundation of this structure. So this is the reason why the shear strength is the strength which is determinant in soil mechanics. And this is the reason why this Mohr-Coulomb failure criteria that take into account the shear strength is so famous and is so effective, because this is what happened in reality. Now we're going to try to explain what is the foundation function and what are the type of foundations we can study in geotechnical engineering design. So in the first place, we need to say that the purpose of a foundation is simple to transmit the structural loading from the building and to spread this load on the ground, because the ground has to take all the loads coming from the buildings. The loads that are produced by the wind, the loads are produced by the self-weight, the load that is produced by the use, the load that is produced for any other reason has to be transmitted and spread on the soil. So the mission of the foundations is a very important mission, is to spread the load from the building to the ground. the final destination of the forces, the external forces that are applied on our buildings and constructions. There are several types of foundations, and we are going to study certainly just a few of them. But we are going to classify this in shallow foundation and deep foundations. So in terms of shallow foundations, the first one I wanted to share with you, the first one I wanted to show you is the pad footing. The pad footing is a very popular foundation. It's a very popular shallow foundation in buildings and consists in these elements you can see in the picture that are individuals and isolated foundations that are called pad footings, and they can be a square or they can be rectangular. They can be circular. They can have any shape, but the most popular one are the rectangular and the square ones. The columns that apply the forces on this foundation can be center columns like this, or can be asymmetric. I'm not sure if I'm seeing any eccentric column on this foundation, but you can have the case that you have eccentric or double eccentric column applied to pad footings. So as you see, it's very clear that this is a shallow foundation because the foundation is very close to the surface, to the ground. So this is the reason why they are called shallow foundations. The second type of foundation is the street footing. The street footing is, let's say, an evolution of the pad foundation because it's in the case where you have several columns next to each other and very close to each other, or when you have a wall that needs to be founded. So in this case, the footing is a street footing. Also, it's an structure that has this cross section, as you can see here, that could be in this shape, a combination of a trapezium and a rectangle, or just a rectangle. And after that, you have a strip that is several meters long in many cases. You have more details about this foundation and the previous one in these YouTube links that you can see by yourself and to enjoy, to understand a little bit more what is this kind of this type of foundation about. So there is a third foundation that are in this classification of shallow foundations when the soil is not too strong, or when you just have a lot of loads from the buildings. Maybe you need a lot of more surface to spread these loads on the ground. And in these cases, you use what we call a raft foundation, which is basically a slab that is on the floor to spread the load from the building. As you see, the raft foundation is not a very popular foundation because it's very costly. It's costly because it takes a lot of material to be done, a lot of concrete, a lot of reinforcements, because this is basically the size of the building that has to be founded on the ground directly. So, of course, preferably, if we can use isolated foundation like pad foundation or these strip foundations, it's gonna be cheaper, but these foundations are sometimes the only solution we find in order to spread the loads from the building in an effective way for many reasons. For example, because the soil is not too strong, or because the loads from the building are too high. You have another link in here to see more details about the raft foundations. The next type of foundation, the next classification, is the deep foundation. This is another thing we're going to study in this course. And basically, for deep foundation, we are going to study piles only, and two types of piles. The first type is called bore piles. This bore piles is called in this way because you need to bore first to install the piles, and you have in here 5 different phases on the installation of the bore pile. So you have to introduce first in the soil, in the ground, a casing, or you have to install the casing. After that, you have to drill to create the hole. After that, you install the reinforcement, and the reason why you have a casing is because you want to clean the area where you are going to apply, you are going to introduce or install the reinforcement, and after you are going to pour the concrete. And finally, once the pipe is ready to work, you can extract and reuse the casing for another pile. So this is the bore pile, and this last one, the last foundation we're going to study in this course, and the last foundation I want to show you in this video, is the driven piles. This is the funnier one. If you want to see this video, you will have fun seeing how these driven piles are installed, because they are hammering basically on the soil, and it's a very effective system to found buildings, tall buildings, because produce not only the spread of the forces by two mechanisms, the friction and the bearing capacity at the tip of the pile, but produce as well a consolidation on the soil, improving considerably the strength of the soil are in the area of the foundation of any building. So now we have discussed the three main concepts around foundation, which are the effective stress, the failure criteria, and we have discussed as well the types of foundation. It's time to discuss the bearing capacity. The bearing capacity is the capacity of the soil to take loads. So we need to establish in some way how much capacity we have for every case, in order to compare with the loads that are coming from the building and be sure that we have enough bearing capacity to support the loads that are coming from the building. So we are going to start studying in this video the concept around shallow foundations only. And the shallow foundation we are going to use to drive our explanation is the street footing. For this reason, we are going to consider that we are analyzing a meter depth, because this is a footing that had several meters, but we are going to do the analysis only in 1 meter, because it's going to be the same in the rest of the depth or the rest of the dimension of the street footing. You can apply the same principles and the same formulas to a pad foundation, just simple changing this meter in here for the actual dimension of the pad footing. So basically, the bearing capacity we are going to call Q is a stress. And a stress then measured in kilonewton per square meters or newton per square millimeters. And we are going to make another big assumption in here. We are going to assume that this stress is an UDL. So the contact between the foundation and the soil will generate a reaction from the ground that is going to have this shape. So it's going to be an uniformly distributed load. This is not exactly true, because in reality, because the characteristics and the properties of the soil, this distribution will be certainly non-linear. But by just because we need to simplify the calculation, we're going to use this distribution. And anyway, the values we are going to obtain are sensible and can be used certainly to design and to verify foundations like this. So on this foundation, we are going to have a small Q, which is a force per meter, because we are considering a meter depth. And this is the force that is coming from the building, for a wall, for example. We are going to have as well the self-weights of the structure plus the self-weights of the soil on top of the structure in this area and in this area. And this is the reason why we are going to use this unit weight average, which is the unit weight average between the soil and the foundation. And this will allow us to calculate the W, which is the weight, the self-weight of the foundation and the soil. This dimension here, the depth where we are installing the street footing, is D in meters, and this is the dimension of the width of the foundation we are going to call B in meters as well. The theoretical important thing you need to know for this simple calculation we are discussing in this video is that we have a formula that we can be confident to use about the bearing capacity of this type of foundations, and for every foundation actually, that have a lot of developments from many authors during many years, and is based on the plasticity theory. So it's a very complex theory that we are not able to discuss in this video, but basically we arrived to this formula, which is certainly simple, that have several factors to be considered. We have the cohesion, for example, that multiplied to this coefficient MC. We are going to see how to calculate. Plus the second term is gamma, which is the unit weight of the soil under the foundation. D is this dimension in here, as you can see. NQ is another coefficient we are going to calculate with the funny formula. Plus half of the unit weight multiplied by B, the dimension of the width of this foundation, and multiplied by the last and third coefficient and gamma that we are going to determine for different cases. So this is the formula we're going to use for bearing capacity, for determine the bearing capacity of a street foundation or a pad foundation. and let's see different cases we can deal with. So the first situation we can have, for example, is the situation where we have clay and the situation is drain. When you combine these two words, apparently there is a kind of a problem in here because there is a contradiction. We have clay, we know that the clay is almost impervious when it's wet, but we have the situation which is drain. Automatically, when we read something like this, we think that if the situation is drain, probably there is some sand that is contributing with some angle of internal friction to the strength, and the sand is contributing with some permeability. So automatically we know that we are going to have as a data some angle of internal friction. And with this angle of internal friction, we are going to calculate these three coefficients I mentioned before, and in our formula are here, NC, NQ, and gamma. So if we replace the value of the angle of internal friction in these formulas, we are going to be able to determine these coefficients. The cohesion will be a cohesion that will be a data and will be affected by some reduction coefficient from the Eurocode 7. We are going to see this in the problem in the next video. And the angle of internal friction is going to be affected as well by a reduction coefficient by the Eurocode 7. So once we apply these formulas and once we reduce the properties of the soil, the clay and the sand, this is clay and this is sand, affected by the coefficient, reduction coefficient for the Eurocode, we are going to be ready to determine the bearing capacity of this foundation. Remember that the dimension, this is the depth and this is the width of the foundation, and Q, small q, is the loads that is coming from the building. The other case we can have is the case where we have clay and drain. In this situation, we have only clay because evidently if the situation is undrained, this means that there is not any sand present. And because there is not any sand present, we are going to lose the terms related with the angle of internal friction, because the angle of internal friction is going to be equal to 0. And this will make some troubles in here, because if you check the formulas for determine these coefficients NC, NQ, and N gamma, you see that, for example, the first one, NC, when you replace 0 in this factor in here affected by the cotangent, we are going to have an infinite number as a result, which is indeterminate. So this cannot be used. If we replace the values of 5 in this second expression for NQ, we find that NQ is equal to 1. And if we replace the value in N gamma, we find that the value is equal to 0. So this is the reason why we are going to lose the last terms of the general equation in here, because N gamma is equal to 0. And the formula for our bearing capacity for the clay and drain is going to be simpler because we only have two terms in here. The Eurocode recommends to use for NQ1, and this is logical because if you replace the value of phi equal to 0 in this expression, you obtain 1, and N gamma is equal to 0 as well for the same reason. But for NC, because we cannot use an infinite as a value, we are going to follow the approach of the Eurocode that say that this value had to be calculated as 2 plus pi, which is 6.28. And of course, as you noted already, all the values of these coefficients are adimensional. Okay, and this is what makes this equation consistent, because Q is an stress, SU is an stress, for example, and the multiplication of gamma times D is an stress as well. And these two guys in here, NC and NQ, are adimensional. We are going to use for this case where we have clay and drain, a cohesion, and the cohesion can be used or can be equal to the clay strength directly, as is shown in this simple equation. You can affect, of course, the clay strength by the Eurocode's reduction coefficients we are going to study in the problem in the next video. But you see that for this case, the formula at least is simpler. When you have a case where you have only sand and the situation is drained in this case, because there is not any clay producing any reduction in the permeability, automatically we know that the cohesion is equal to 0, and we are going to lose the first terms of the general equations. If you remember, the general equation includes 3 terms, and the first one is cohesion times NC. Because the cohesion is equal to 0, we lose the first term, and we work only with the second and the third term. We know that the angle of internal friction will be reduced by the Euro code. We are going to see how to do it in the next video. And we can start, calculating our coefficients, our adimensional coefficients, but NC is useless because it's going to be multiplied by 0 anyway. So we need to calculate only NQ and N gamma. When we calculate these values, which are adimensional, we can replace in the formula, and because we have all the other data, we can establish the bearing capacity. Now, to end this video, we're going to see 3 different cases, taking in consideration the different position that the water table can have. So the first situation, and I have to add regarding the other 3 cases we've been discussing, in all these cases we have been discussing different types of soils. We have considered that the water table is far from the foundation, so there is not any water involved, and for this reason we didn't mention anything about this gamma, which is the dry unit weight for every case. So, but now we are studying the effect of the water table position. So the first one is when the water table position is far from the foundation, so it is farther than D plus B. Sorry for that. So it's farther than the distance D plus B. And in this case, the gamma we're going to use is the dry gamma, the dry unit weight for the soil under the foundation, because the water table is not affecting the area where we are determining the bearing capacity. So in this case, if we try to relate this explanation with the definition of the effective stress, what is happening is, because the situation or the soil is dry, we are saying that the total stress is equal to the effective stress, and for this reason we don't need to introduce any change in this formula. We just need to apply the formula with this gamma, which is the dry unit weight for the soil. In a situation where the water table is closer to the foundation, but this is at a distance that is greater than D but is smaller than D plus B, so the position is shown in here in this screen, we have to use gamma for NQ. NQ is this second term in here, and is related with this distance D in here. So in this area we are pretty sure that the soil is dry, and we need to use gamma minus gamma water for the terms N gamma, because in this area under the foundation we are going to have certainly a wet soil, because we have the soil that is under the water table, and the soil on top of the water table will be wet as well because the capillary effects. So for this term that is related with this area under the foundation, we're going to use gamma. Instead of gamma, we're going to use gamma minus gamma water, or gamma W, which means that we are applying in there the effective stress instead of the total stress. Or what is the same, we are saying that in this area where we are far from the water table, we are applying gamma, because this is the case where the total stress is equal to the effective stress. And in the case under the situation with the water table very close, we are going to have a situation where we need to use the effective stress. And for this reason, we are going to replace directly gamma by gamma minus gamma W, which is the difference between the, let's say, the total stress minus the water pressure, as in the definition of the effective stress I have shown at the beginning of this video. The last case we're going to study, or that we're going to discuss, is the case where the water table is very close to the surface. So in this case, because the capillary effect, all this area in here on top of the water table is wet, and all the area under the water table is wet as well. So in this case, the situation is that we are being affected by the effective stress in all the cases, in every layer or in every depth of this calculation. And for this reason, we are going to use gamma minus gamma W for both cases, for the second terms and for the third terms of the bearing capacity calculation, because in this case we are dealing directly with the effective stress. When we are working with this difference between the dry gamma and the dry unit weight and the unit weight of the water, what we are doing is we are using the effective stress. So just to clarify what is the idea behind this analysis, you see that we have been determining with different formulas the bearing capacity of the soil. And this is the situation. It's a very, very simple situation where you have a load coming from a building, you have the self-weight of the foundation, including the soil, and you have the reaction of the ground. So the reaction you have on the ground needs to be a reaction that is possible to be implemented, and this is the bearing capacity. If the soil is strong enough, the soil will be able to produce this reaction without any problem. But if the soil reaches its strain, the soil will be broken and the foundation will fail. So in order to avoid this failure, what we do is we use the summation of forces in the vertical direction. So what we are doing is basically we are using the principle of equilibrium, and we say that the load coming from the building plus the self-weight of the foundation has to be equal to the bearing capacity multiplied by B, because remember that the bearing capacity is a stress. So multiplying by B, we are going to have a force per meter, which is equal to the force that is acting on this foundation, which is a force per meter, and is equal to the self-weight of the foundation and the soil, which is a force per meter as well. So this is our equation of equilibrium. So if we reach the equilibrium, we are in good conditions. If we are not in equilibrium because we need more bearing capacity, we are not in equilibrium. So we need to redesign the value of B in order to reach the equilibrium and in order to spread the load from the building in a proper way. So if we want to design a foundation, we can use this equilibrium equation and work out the value of V, as I did in here, to calculate how much B in meters we need to take the forces from the building and the self-weight of the foundation. So this is a very, very simple approach based on equilibriums in the vertical direction, because this is the mechanism we are saying that will be the mechanism of failure. So we are going to have a bearing capacity that has to be able to take the load from the buildings and the self-weight of the foundation. So this is all for this video. I hope everything is clear, and see you in the next one. Thank you very much.